Okay, assalamu alaikum, everyone. Welcome to today's class on power system modeling. So, in the last class, we were going through basically in the last portion of the last lecture, we were discussing about the phasor diagram, okay? Construction of the phasor diagram for a network such as this, where we have a single machine and that is connected to a large network that is represented by an infinite bus. And in between, we have a transmission link. So the generator is generating the real power PT, and QT is the reactive power, and the current injected by the generator into the terminal of the generator that is having a voltage VT. So the current produced by the generator is IT. And as we said that these IT, VT, and VB, these are phasors. Okay, so they have angles as well as the magnitude. So in the last class, we defined our steady space model as a sample system for a sample system of an initial value problem. Okay, initial value problem. So we had a system of ODEs, and we were trying to solve basically for the time domain responses for the system under consideration. So the summary of the equations we took in the last class, this, okay, in slide number 41. So this is the third order model, and we were trying to obtain basically delta versus time, omega versus time, as well as EQ dash versus time. So in general, for solving this sort of problem, that is the order of ODEs, because these are differential equation. So in general, to solve the differential equation, we usually adopt the integration technique, okay? The reverse process of the differentiation. So we will also apply the integration technique, and the family of that integration technique, we will call it as numerical integration. So while we apply this, then we will see that, well, after application of this numerical integration for this model over here, we will be able to obtain these three responses. Besides, there will be other responses achievable from these three responses, which are, or which could be represented as some functions of these three, okay, delta, omega, and EQ prime. For example, once we are able to achieve this delta versus time and EQ prime versus time, then we will be also able to plot PT versus time, as well as the QT versus time, and other parameters of the network, such as the IT, the current out of the generator versus time. Those will all become possible then, once we achieve these three with the help of the numerical integration technique, and as well as VT versus time. So all we can calculate. So that is the beauty of the numerical integration technique. While we apply that to this model, we will be able to achieve all these things. But before that, we have to calculate, we have to start from a certain operating condition or operating point, okay? We have to start the numerical integration from a certain operating point. So for any dynamic system, the operating point means that any relationship between these variables, that means once we are able to achieve, let's say this is a trajectory of any variable x with respect to time, okay? And there could be x1, x2, and so on. So by operating condition or operating point, we mean any point which satisfies this relationship between x1 and t. That means any point which lies on this trajectory. Okay. So this is in general the definition of operating point. So basically we are looking for the operating point, which we will denote by the equilibrium point or steady state operating point. So the steady state operating point or the equilibrium point is a special case for the in general operating point, okay? So the equilibrium point or the steady state operating point is that point, that operating point where all the dynamics are equated to 0. So that means the system is in a steady state. So the steady state operating point or the equilibrium point is nothing but one special case of the in generalized operating point, whereas operating point can be any point on the trajectory on the solution of x as a function of time, because the equation is as a function of time. So basically we are looking for, first of all, we are saying the initial condition. So by that initial condition, we mean we are looking for that equilibrium point. So that is our first target today. Okay, so let's start with the equilibrium point. Once we are done with the equilibrium point calculation, then we'll be able to apply the numerical integration technique, and then that will help us to calculate all these things over here and over here. So the first step is, for any solution of any dynamic system or any ODE system of ODEs, the first step is to calculate the equilibrium point or the operating point. If it is given, then it's fine. If it is not given, if it is not explicitly given, then we have to identify the values of the variables under consideration with the help of the calculation of the equilibrium point. So while trying to calculate the initial condition or the equilibrium point, we will take help of the phasor diagram. So let us see how we can draw the phasor diagram for our network SMIB system. So this was the network on the left, and on the right, this is the phasor diagram. So let's take an enlarged view, because that is too small, I think, the font. Now I think it is clearer. Can you understand clearly what is written on the right here within the block?
Yes.
Yeah. Okay. So let's start. So in general, to find out the initial operating point or the initial operating condition, initially you need to know at least some values with respect to the network, related to the network. So those values, let's say, those values should be given or should be available, or you should be able to calculate it beforehand. For a very large network, we generally take help of the load flow analysis to know these values at each bus. But for this system, we will assume that, well, these values are given. Okay, this is the initial, some of the points related to the initial operating condition. So we know how much power is being generated by the generator, real power is generated by the generator. What is the power factor of the power that is supplied by the generator, or what is the reactive power supplied by the generator? All the same. If we know the power factor, we can calculate Q if P is given and power factor is given. On the other hand, if both P and Q are given, we can also calculate the power factor. So if you know two of those, then the other can be easily calculated. Then we will assume that, well, the VT magnitude is at least known, and VB magnitude is at least known. So these are the phasors. So these are the magnitudes of the absolute value of the phasors. So with this assumption, we will start our next steps of calculation. So let's start at this bus, because we know, what do you know at this bus? Let's see. And what do you know at this bus? So on the left side, this bus, whose terminal voltage is VT, we know the PT, we know the QT, and we know the VT. So using these three information, we can easily calculate IT. Okay, before that, let's simultaneously, we will try to build up these phasor diagram on the right. So without loss of generality, we will assume that these VT, to start with, this VT is our phasor which is lying at 0 degree. Okay, so we will draw it horizontal to the horizontal for the horizontal line for the overall system. So that means we are actually assuming, to start with, this is our reference. Later on, we will switch the reference. Okay, later on we will see that no, this is actually the reference, but it doesn't matter. If we know one, then we can calculate the other very easily. So to start with, we will assume that okay, we don't know the angle of VT. Okay, we don't know the angle of VT. So this angle is considered initially to be the angle 0 without loss of generality. So it's all the same. If you consider this to be 0, VB to be 0, then VT will be some positive angle, right? This would be VT. On the other hand, if you consider VT to be the reference, then VB will have some negative angle. That's it. That's the difference. So it's not a big deal. Okay, we can assume any of those as the reference. But to build up the phasor diagram, in general, we are provided with this information: PT, QT, and VT and VB. In general, these four are given, the magnitude of VT and VB. So we will start with VT as our initial reference. Okay, so then with the above mentioned information provided here, these three, we will be able to calculate IT. What would be IT? IT would be PT minus JQT over VT conjugate. Okay. So from where are you getting this? Can anyone explain?
Sir, S equal to VI conjugate.
Yeah, S equals to VI conjugate. So this is the origin basically, VI conjugate. This is in the phasor form, of course, not in this instantaneous form. Instantaneous form, it is VI or VAIA plus VBIB plus VCIC, like that. So then if I want I, so simply I have to, if I want I, then simply I have to take the conjugate for all, and I can take S conjugate over V conjugate. So that is the background. And S, as we know, S on its own, it is P plus JQ. So if I take the conjugate of this, so then simply the real, the imaginary part will change its sign if it is, if it is represented in rectangular form. In the polar form, the angle will change its sign. However, we are taking the rectangular representation. So the plus sign will become minus. So simply IT is equal to PT minus JQT over VT conjugate. But because we are taking VT initially to be at some angle 0, so we don't have to bother about the conjugate term here. So from here, we can get the magnitude of IT. Now, what about the angle? Because of the minus here, we will see that there is some angle. Let's say that is the power factor angle, and that angle will be associated with a minus sign. So initially what we will do, we are drawing the VT first, and then we draw the IT. Can you follow the IT here? This is our IT, which is at an angle theta lagging from the reference, initial reference VT. So this is our first part of the calculation. We get the IT. Next, what we do, so IT is done. The next step, once we know the IT, can we get VB from that? If you know IT, can we get VB, phasor VB? What would be VB? Phasor VB. We know IT, we know this is the reactance, inductive reactance, and we know IT. So VB would be simply VT phasor minus, because the current is coming out of VT, so there will be drop in voltage. So that is J XT into IT. Okay. So again, that would be some angle lagging because of this minus sign. That would be some angle lagging from the initial reference VT. So this is VB, and we take this angle as this angle, delta 2. Okay. So this is our angle minus delta 2. So that means now we also have this VB phasor done. So we have got VT, we started with VT, we have got IT, and with the help of IT, we have got VB. So what we are doing simply, we are calculating JXT IT. So JXT IT would be where? And remember, that is a minus sign. So JXT IT is subtracted from phasor VT. So this was the VT, and when we subtract, we take in this direction, and that is 90-degree with the phasor IT. Okay. Because it is an inductive reactance, so current would be lagging, voltage would be leading. So this is JXT-IT. This is the voltage across this reactance, and that is IT. And then we draw JXT-IT from the tip of VT. So this is VT minus JXT-IT, and we reach here, that is VB. And then we draw the phasor VB from the origin of the phasor diagram. That is the origin of the phasor diagram. We just connect it and we get VB with an angle delta 2 lagging from VT in this case. So we are done with VB. The next step is a little tricky, because in the next step, what we are doing, we are trying to find out the location of Q axis. So in the next step, what we are doing simply, you see, this is the Q axis, this enlarged big line, this is the Q axis. And if you look at it carefully, what we are doing, we are simply adding, this is our original VT. We are simply adding this phasor JXQIT with VT. Again, JXQIT would be 90-degree phase shift with the phasor IT because of this J. Okay. So JXQIT would be added up the phasor addition with VT, and you reach somewhere to some phasor known as EQ capital. Okay, we haven't seen this yet, so we will discuss it, how we are going to get it. So this VT plus JXQ, this is new for us. Okay, I will explain it now. So when I calculate this addition, phasor addition, then I say that, well, I have reached at some phasor known as EQ, and we will see that this EQ actually lies along the Q axis. Okay, so we will see that. But to reach at the Q axis, the relation that we have to use is this. Remember, we are ignoring all the resistive elements here. There are no resistive elements. If you have any resistive element, then simply you have to add up this thing, RA plus JXQ. Remember this, RA plus JXQ into IT then. So you don't have RA is 0. So simply what we are doing, we are adding JXQIT phasor with the phasor VT to reach at the Q axis, or to reach at a phasor known as E capital Q. So once we are able to locate Q axis, then the job is actually done. But before that, before decomposing all the phasors into its D and Q components, let's try to find out what is this EQ. Okay. So let's start with the known expressions of VD and VQ. Remember, we already know what is VD in terms of ID, IQ, and we also know VQ in terms of EQ and IQ or ID. Let's bring those relations from our previous derivations. So what we are simply doing in the first line for locating the Q axis, this is the basic explanation, actually, the background explanation for why we are saying that, well, if I add up JXQIT with VT, I get to the Q axis. Okay, this is the explanation. So first of all, what we do, we take VD and VQ expression. So VD is XQIQ. So we derived it earlier. So let's go there. So you see in slide 44, VD is XQIQ. So we take this expression and we take this expression. These are already derived, so I'm not going to explain those again. And what we will do, we will simply add those as the components of a phasor. So VD, we will assume that this is the D component of a phasor known as the terminal voltage. Remember, VD and VQ are nothing but the resulting D and Q component of a phasor VT, the terminal voltage. Or we can also say it is the result of VA, VB, VC, those three-phase quantities being transformed to D and Q axis. So this is VA, VB, VC was the ABC reference frame variables for the voltage, When we applied DQ0 transformation, then we obtained actually VD, VQ, and V0. But 0 was actually not considered further because considering it is a balanced system. So these VA, VB, BC are nothing but the your instantaneous voltages. And when we take the phasor, this is our phasor VT, the terminal voltage. So VD plus JVQ. So to get this VD plus JVQ, what we have to do, we have to take it as it is, XQIQ, and then plus J into this EQ minus XDIT. So this is what we will do. What we will achieve after doing that, so you see VD plus JVQ, it is the rectangular representation of the phasor VT along its D and Q axis components, or with the help of the D and Q axis components for the phasor VT, we can write it. So VD plus JVQ, once we get it, we can easily write it as the phasor VT. So this is why we start with this calculation. So this is what we are doing, just what I mentioned. VD plus JVQ is XQIQ, where XQIQ is VD plus JVQ is EQ minus XDIT. Now, what is actually EQ? Can anyone tell? I mean, from the name, can you get some idea or give some idea? From the notation. Let's say if you had, instead of EQ, if you had ED, what should come to your mind at first? Along which axis is it aligned? And along which axis is this aligned? E stands for some voltage, right? So E is a voltage, internal voltage, some sort of internal voltage. The Q means this EQ should be lying along the Q axis, isn't it?
Yes, sir.
So whatever it is, whatever type of voltage it is, be it internal voltage or whatever voltage inside the machine, but it should be lying along the Q axis. This is one of the very important conclusion from the notation that we can, or one of the very important idea that we can get just by looking at the symbol EQ. Instead, if we had ED, we could conclude that, well, that is along the D axis. Okay. So now with this little concept about EQ or its location, let's proceed. So XQIQ, we can write it like minus J square XQIQ, where J is the imaginary operator, J is square root of -1. So when you take square, then the square root goes out, we have J square equals to -1, and when we multiply with another minus, so you again go back here. So it is simply, we are bringing it for our calculation purpose. Then we have JEQ, and then what we are doing, we are simply adding these two terms. So the first two terms are already there, that is JEQ minus JXDID. We are adding up and subtracting these two. Okay, this is basically the trick behind this phasor notation calculation or this calculation. So this is the trick. We are adding up some extra terms in our or along our derivation. Okay, so once we do that, then what we will try to do, because on the left hand side we see this is nothing but VT. This is the phasor VT decomposed into D and Q axis components. So this is the phasor VT. So here we have IQ. So if somehow we can find something in the form like this, ID plus JIQ, right? Then we will be able to say, well, this is again another phasor IT, isn't it? This is another phasor IT. So basically the things that we are doing here, we are bringing some additional terms and subtracting it again, just to bring this ID plus JIQ form, so that we can use up this notation, phasor notation. That's why we are bringing these things, okay? So now let's see. So we bring JEQ first, minus JXQ. So we take JXQ from here and we JXQ from here. So you group them and you find that, well, if it is minus JXQ, then you can have minus JXQ ID minus J square XQ IQ. So one term is this, the second term, and the first term is actually this JXQ ID minus JXQ ID. This term is this one, the first one. So what is left? This is left. So we simply write JID, and then you see it is XQ minus XD. So all terms are taken care of. So we reach here. Then we see, well, we have ID plus JIQ, and our target is achieved. We can represent it in terms of phasor IT, some terminal quantities, or some quantities which can be measured at the terminal of the machine. Okay, these are available at the terminal. VT, it is available at the terminal. We can measure it with the help of any voltage measuring device. IT, it is measurable. It is at the terminal. You can measure it with any current measuring device. So these are physically available parameters, physically available or physically measurable quantities. These are nothing internal to the machine. These are not ID and IQ. These are phasors, or these are quantities that you can measure easily. So VD plus JVQ, and then what we do, we bring this minus JXQ ID plus IQ on the left hand side, and we keep the remaining on the right hand side. So you see that on the right hand side we have all with some J. Okay, some J operator, and then we have some expression in terms of ID, XD, and XQ. So then what we do, we see that, well, the first term over here, this is VT. This term is IT. And we are left with JXQ. So this part is done. So we have reached here. You see, on the left hand side, whatever we have written, that has already arrived here. VT plus JXQ IT. Now we actually define the whole thing by this EQ. So this is some hypothetical EMF. You can call it as some hypothetical EMF, phasor EQ, E capital Q, or imaginary EMF, Now, why we are calling it E along some Q axis? Because you see the components that we have internal to this expression. The first component, along which axis should it lie?
Q axis.
Q axis. So you see, this is along Q axis. And there is another term in addition to this, addition or subtraction, whatever you say. In addition to that, we have another component here within the J, bracketed J term, that don't have any further phase shift from EQ, right? So EQ, and then you see there is no J with that. So whatever will be the direction of EQ in the phasor diagram, the same direction should apply for this. Is this clear? Usually in the phasor diagram, we have this sort of phase shifts, okay? Either with plus J or with minus J. There are only two ways, okay, for phase shifting. I mean, in terms of J operator. So this EQ, because it is lying along the Q axis, and because for the second term, there are no other J or J squared plus or minus with that. So we can say easily that the second term also should lie along Q axis. Is this clear? The last line that I just mentioned. What is this? What is this? What would you get if you multiply some reactance with some current? You get some voltage, right? It is like I into X, some I into X, whatever, D or Q, whatever. So I'm talking about the alignment of the second portion. Actually, where it is lying, along which axis it is actually lying. Okay. So let me explain again. This, the first term, there is no confusion. It is along the q-axis. There is no confusion about that. The confusion is about the second term. And I say, well, this and EQ should lie along the same line, along the same axis on the phasor diagram, because they don't have any phase shift between them. Okay. If they had any phase shift, then you would expect some J inside, J or J square. Because they don't have anything, so they should lie along the q-axis. Both of these two should lie along the q-axis. So they will combine and they would give me some other voltage, and that should be also along the q-axis. So what I do, I simply drop the J term and I take J inside the expression of EQ phasor. So I'm writing it as a phasor. So remember all these things, VD, VQ, these are DC components. These are not phasors. ID, IQ. These are DC components. EQ, this is a DC component that is lying along the q-axis. ID, it is a DC component. That means it is a component of the original phasor. Whereas EQ bar, it is a phasor. Okay, so you can also think about this EQ bar, something like this: 0 plus whatever you have here, 0 plus J multiplied by EQ minus XD minus XQ into ID. Okay, you can also think it like this. So then you say there is some real part having a 0. So real part plus imaginary part into this. So this thing, whole thing, I can write it as another phasor, and we are taking the phasor notation as this EQ. Okay. So all these things within this bracket should lie along the q-axis, because EQ is along the q-axis.
Sir, if all those terms lie along the q-axis and we multiply it with J, then can we say that this now is along the axis?
No, because on the right hand side, on the left hand side, you have to see what is going on. On the left hand side, what did we write? VD plus JVQ. Remember? So we simply equate them.
Okay, sir. Yes, I got it.
Oh, you get it. Okay. Because there is something 0 plus some J. Okay. So this J and this J, you can compare. That means if VQ is along the q-axis, so whatever with J, that should be along the q-axis. That's
yes.
it. Okay. Thank you. So this is how we can reach and we can find the location of the q-axis with some little trick in between. And once we are able to find the q-axis, then we say that, well, we are done, almost done. Because once you can locate the q-axis, you can easily, very easily locate the d-axis, because d and q-axis always they have a 90-degree phase difference between them. So let's move on with this discussion. So we calculated which phasors earlier? We calculated VT. VT was done. VB was done. IT was done. Now we say VT plus JXQ IT will take me to some point which lies along the q-axis. Okay. And the phasor that I will get from the origin, that is E capital Q phasor. That's it. And this direction is the direction of q-axis starting from the origin. So what would be the d-axis? We assume that d-axis is 90-degree lagging. So this is the d-axis, 90-degree lagging. So once you locate the q-axis, then it is pretty straightforward. So this is your d-axis. Okay, this is the d-axis. So we are done with the location of q-axis as well as the d-axis. Now we define our power angle or torque angle or rotor angle, whatever you say, that is calculated or that is measured from the reference. Okay, so the power angle or the rotor angle is measured from a reference, and now we say, well, this is our original reference for the whole system. Okay, VB is the reference. Although VT, we assume that it is lying along 0 degree, but in that case, VB will be some negative angle. Okay, and for this diagram, it is VB minus delta 2. It doesn't matter, but this is the actual reference. Okay, so with that, what we will do now, we have VB angle minus delta 2 and delta 1. So when we draw the Q axis, we define another angle. So what we do basically is this: VT phasor plus JXQ IT should give me the Q axis, and that is the phasor E capital Q. And if I write in terms of magnitude, so I will write it like this: EQ magnitude with an angle delta 1. So you see, this is the angle delta 1, that should be positive. Okay, this is the delta 1 because this is the Q axis and this is my initial reference VT, which is at an angle 0. Okay, so this is delta 1. So we have got delta 1, we have got delta 2, we have got theta. So what is left is the last angle here, that is delta. So delta is the angle measured from VB, that is the infinite bus or the reference bus for the system. And it is the angle between Q axis and your VB phasor. Okay, that is the angle delta. This is the definition of delta. The power angle, we call it power angle or rotor angle or torque angle. All these are same. So this should give you the initial value of your state variable delta. Remember, delta dot was one of your expression. So delta is one of your state variable. So when you will be able to calculate this delta, you will know what is your delta initial value. Okay, delta 0 or delta 1, whatever you call it. The first value of delta at a steady state, you will be able to calculate, you will be able to know that value. So once we calculate EQ, we find that the corresponding angle for that phasor EQ is delta 1. And then we can easily draw the delta only. Okay, the delta is the angle between VB and Q axis. So once you look at the Q axis, if you know VB, then you can easily calculate the delta. So from the phasor diagram, what would be delta? You can also say that, well, angle delta is nothing but the angle delta 1. So angle delta is angle delta 1. Then what?
Delta 2 plus delta 2.
Plus delta 2, but remember delta 2 was negative, so you have to take the absolute value because delta 2 would come as negative. Okay, because VT is at angle 0, that's why. So the absolute value of delta 2 plus delta 1 will give you the numeric value of delta. So that is your initial value of delta. One of the state variable initial value is already obtained using the phasor diagram. So once you are done with delta, then the life is pretty simple. In the next steps, like this, that you have all the phasors drawn. Now you can easily calculate the VD, ID, VQ, IQ, VBD, IB, VBD, VBQ, all these things. So how to do that? Let's see. So how do you calculate now? Let's say VQ. What should be VQ? Anyone? Quickly. It is a component of VT. So it is the component of phasor VT, absolute of VT. Then what is the angle between VT and Q axis?
Delta 1.
Delta 1. So it should be cosine component. Okay, cosine delta 1. What about VD? It is VT
VT sine delta.
sine delta 1. Excellent. Let's move on. What is ID or IQ? Let's take Q first. So it is delta 1 plus theta 1, right? This is the angle which covers delta 1 plus absolute value of theta, isn't it? Can you locate the angle between Q axis and IT? This is IT. The angle between IT and VT is theta, which is lagging, so which is minus. And the angle between VT and EQ, Q axis is delta 1. So the total angle is delta 1 plus absolute value of theta. Okay. Any confusion, please stop me and ask me questions. So cosine delta 1 plus absolute value of theta 1. What is ID? Is IT, then sine, the same thing. Okay, VD, ID, VQ, IQ. Then what's left? VBD. What is VBD? Or let's say VBQ first. What should be VBQ? What is the angle between VB and Q axis?
Delta.
Delta.
Delta. So VB, remember we assume that we know the actually the initial magnitude of VB, or even we don't know it, we can calculate it as I showed. VB equals VT minus J XT IT, right? So from there we can also pick the magnitude of this phasor, and that would be used here. VB magnitude into cosine delta, and VBD would be VB magnitude sine, this is VB sine of delta. And these are the important steps for calculating the DQ components as well as drawing the phasor diagram. Okay. Once we are done up to this step, then we have to go through some checking. What are the checkings? The checkings are this. So whether our calculations are correct or not, we can check it by the help of the calculation of PT again. Remember, we started from some PT value, right? We started from some PT, known value of PT, QT, and VT, a magnitude. So these were given initially. So what we will do after this, just for our satisfaction, okay, whether these phasor diagram, drawing of the phasor diagram, or extraction of the angles, or calculation of the components, whether all of these are correct or not, what we will do, we will use the relations that we derived earlier, that is VDID plus VQIQ for PT. Let's make it capital because we have been using capital throughout the lecture. So VQIQ. Okay. So you see here on the left block, you have VQ, value of VQ, value of VD, value of IQ, value of ID. So all four are calculated. You just plug them in, and that should be the same as this value. If that's same, then you are satisfied. Well, this is done. Come to QT. QT expression was obtained as this: VQID minus VDIQ. This was the calculation for QT, expression of QT. So we started from some QT, so check back again. Okay, just cross check. If these two match, then you are done. VT, we also knew VT initially, VT. So VT magnitude, we are given with VT magnitude. How do you calculate VT magnitude in terms of VD and VQ?
VD square plus VQ square.
Excellent. VD square plus VQ square. So again, you know VD and VQ, you just plug them in. If you get the same VT here, then you are done. You are satisfied. Well, I have done everything correct up till now. Then what's left? We haven't checked ID and IQ individually, but we have checked them here. We can also check them individually. Okay. How do you do that? What is ID and IQ? Just we will go back and check the expressions that we derived in the previous class. So in the slide 44, okay, here you have equation 32 and 33. Okay. So before that, let's see whether we know everything or not. So IQ, can we calculate IQ with whatever values we have obtained till now? Let's see. Do you know VB magnitude? This is magnitude, remember. Do you know VB magnitude? Yes, we know. Do you know delta? Yes, we know. Now we know delta. Initial delta value is known. These two at the bottom are constants. So this should be given. We know those. So IQ, you calculate from equation 32. And IQ, we also obtain from the phasor diagram. So those two IQ should match. Okay. The IQ obtained from the phasor diagram and IQ that will be obtained from 32, they should match. Then IQ part is okay. What about ID? Do you know VB magnitude? Yes, we know. Do you know delta? Yes, that is known. The bottom part is given, should be given, because these are some reactances, system reactances. So that should be given. But do we know EQ dash till now? We don't know EQ dash. Okay. So how do you calculate EQ dash now? you can use this expression here. So EQ dash, you can calculate using this relation over here, VQ plus XD dash ID. Okay. We are using this relation. So then I need EQ dash. So this VQ should be taken from the phasor diagram, ID taken from the phasor diagram. You calculate EQ dash. That phasor diagram calculated value of EQ, you plug it here. Then you see whether this ID and the phasor diagram ID, do they match or not? Okay. If they match, I think you are done. Okay, with your checking even. So now you should be satisfied that, well, your initial condition calculation steps are completely done with 100% accuracy. Okay. So this is how we will calculate the initial value for, and we will draw the phasor diagram for a SMIB system. Okay, any question up to now? No question. So let's solve it. Let's try to solve it using what? Using MATLAB. Okay. So let's start MATLAB. What is that? Yeah, do you see this?
Yes, sir.
Okay, so let's start. Of course, the values that I will take for this will be arbitrary. So, but let's try to follow the steps that we did today. Okay. So, first of all, what we told is that we should be given with some PT value, right? So let's say, and of course, all these values are in per unit. So PT.
Sir, suddenly your voice is too low, sir.
Okay. Do you hear now?
Yes, sir.
Okay. So QT is how much? Let's say it is 0.2. And what else we assumed? We assumed VT. So let's say, remember, this is magnitude of VT. So VT, let's say VTM. So VTM should be what? VTM, let's say 1.0 per unit. These are all assumed values just for demonstrating these steps. So this is your VTM. Now we said that, well, VT is a phasor where the magnitude is given and the angle is how much? Angle is 0. So this is the exponential notation of a phasor. Okay, I hope you know this. So what we are simply doing is this. We are representing VT phasor. Previously, we represented it as this. Okay, VT angle 0, magnitude of VT angle 0. Now what we say, well, the same thing we are representing. This was the polar representation. Same thing, we can do it with the magnitude sign, and we can take it as the power of the exponent, e to the power j theta. So theta here is 0. So this is what we are doing. Okay. So this is what we did there. So this is our VT initially taken as the 0 reference. Then what we did, we calculated IT. This is a phasor. How did we calculate IT? PT minus J QT divided by conjugate of VT phasor. Is it okay? PT minus JQT divided by conjugate of VT should be a bracket. So IT is done. Next, what we did, we calculated VB. Okay, so what was VB? VB was VT phasor minus J into XT into IT. Now the problem is that we don't know XT, so let's assume some value of XT for the time being. Let's say it is 0.25 per unit. So this is our VB. Then we said we will locate the Q axis by calculating some EQ phasor, E capital Q. How did we do that? We took VT plus J into XQ into IT. now we don't know XQ, but we said this should be given. Let's take 0.6, any value. Remember, these are arbitrary. I don't know whether they are meaningful or not, but I'm just taking it for the sake of demonstration. So EQ is VT plus JXQIT. So QXs is located. So now what would be the angles? So let's play with the angles. What was the angle of IT? Theta, right? So theta was the angle of phasor IT. This is theta. What was the angle of phasor VB? Delta 2 probably, right? Delta 2 equals some angle of phasor VB. What was the angle of EQ with respect to the reference phasor VT? That was delta 1. So that is again angle of the phasor E capital Q. Okay, so this is delta 1. So we have got delta 2, we have got theta, we have got delta 1. So what is delta? Delta is delta 1 plus absolute of delta 2, right? Delta 1 plus absolute of delta 2. This is one way. Another way, you can locate the, yeah, this is the way. From the phasor diagram, we got it. Okay, so this is delta. Once we get delta, then we said that now we can decompose our components as our requirement, as per our requirement. So let's decompose VT first. So what was VQ? VQ was absolute of VT phasor multiplied by cosine. And what is the angle of VT and EQ? VT and EQ angle is delta 1. Okay. What is VD? VD is the same with some sine function. So VD and VQ is done. Now we check with IQ and ID. So let's make it IQ, let's make it ID. So what is the angle? So it should be phasor IT, then cosine. What is the angle? It is delta 1 plus absolute of theta, I think. Absolute of theta. Sine delta 1 plus absolute of theta. So this is IQ and ID. Now let's check quickly whether up to this point is it fine or not. VQ IQ plus, okay, we can't use the same symbol, so let's say PT1 just for checking. VD ID. So let's run it. Oh, we have to save it somewhere. Let's name it test SMIB. Okay, so it's not exactly 1. So that means there is some problem. So probably we,
Sir, did you write delta 1?
yeah, because I don't have the diagram in front of me. So IQ is, VQ is delta 1.
The delta 1 is missing. That's why perhaps.
Sorry, which one?
Value of delta 1 you did not write, I think.
Yeah, delta 1 is here.
Sorry, it's okay.
Oh, what did I? Okay, let me check. Oh, I don't know whether I do have those written yet still. Okay, so let's start from I'm just checking back the phasor diagram. So EQ is done, IQ is, VQ is VT cosine delta 1. VQ is VT cosine delta 1. So VD should be VT sine delta 1. That's okay. VB delta 1 plus absolute of delta 2 PT1 IQ. So absolute of IT, absolute of IT sine of delta 1 plus absolute of theta. That is the problem. Don't see any problem here. IT is theta, absolute of theta plus delta 1. VB looks okay. Looks okay. Okay. Let me continue. Just for the time being, let's comment it. Probably there is some error inside. Okay. Let me continue and then I will check again. So this is VQ, VD, IQ, ID. What about EQ dash or EQ prime? Let me check the lecture again. EQ dash is VQ plus XD dash ID. So we need XD dash. So XD prime is, let's say, 0.55. So EQ dash is VQ plus XD dash into ID. So this is EQ dash. What about VBD and VBQ? Take the Q first. So VBQ and VBD respectively. So VBQ, what is VBQ? VBQ should be, let me go back. VBQ is
Absolute value of EB.
Absolute of VB cos delta.
absolute of VB cos delta. That's great. Absolute of VB cos delta. Absolute of VB cosine delta. Okay, so then, okay, so then same thing, absolute of VD, VB into sine delta. So that is our VBD. So VBQ, VBD is done. What's left? The thing that is left is now cross-checking, right? But the first step we couldn't succeed. So let's see. Let's see. Probably I have to check again. But these are the steps actually. This is how you do that. Okay, this is how you do that with the help of the phasor diagram. Okay, let me continue with the checking. So the first thing that we should check is PT. Okay, what about Q? Let's check Q. But because P is not there, I don't know whether VQ will be right or not. Let me check VQ ID minus VD IQ. So this is your QT. Now VT M, let me write VT M1. That would be square root VD square plus VQ square. Okay, this is your VT for checking. QT, PT, VTM. Then we need to check ID and IQ. So let me write something like ID1 and IQ1. ID1 and IQ1. So what is ID1 and IQ1? Let me check the lecture. ID1. Okay. So ID1.
In the line 16, probably it will be absolute of IT.
Oh, yes. Thank you. So yeah, this is the problem. Okay, thank you very much. So because I followed the steps, and that's why you need cross-checking. You see, the benefit of cross-checking we just found today. So there was a mistake. I forgetfully wrote here VT, right? Because it was copied from earlier line. So it remained VT there. I didn't change that. So I think now, inshallah, it will be. Thank you very much. So now we should be able probably, inshallah, to match the results. Okay, so what is IQ? ID, IQ, IQ, IQ is VB sine delta XQ plus XT, VB sine delta. So that is actually VBD. VB sine delta, we can write it in short, XQ plus XT. And that is EQ prime. So there should be a bracket, EQ prime minus, what is there? EQ prime minus VBQ x VBQ divided by XD dash XD prime plus XT. Okay, now let's check. Let's go into the debug mode and put everything in sequence. This is the checking. So starting from line 21, these are for checking. So let's come up to this point first. So we can check, yeah, these are complex quantities. We have some values. Now let's continue with the debug mode. PT1. Yeah, so you see PT1 is 1. Okay. Can you see the value while I go in the debug mode?
Yes, sir.
Okay. How much was QT? QT was 0.2. So QT1 is 0.2. That is done. VTM, it was 1. Remember, it was 1 assumed. So it is done. ID1, 0.5959. So what is ID? Let's go to ID, 0.5959. Okay, so they are matched. What is IQ? The last one, 0.8276. What is IQ there from the phasor? 0.8276. So everything is done. Okay. So this is how you just cross check your initial value computation. And this is the way you do it. And of course, you should do the cross checking part. Otherwise, this kind of problem might happen that we just saw today. Okay. Oh, there were some comments from Sanjida. So thank you. I didn't see that, but probably one of your friend also mentioned it. Okay, so with that, we are done for this part of the lecture, and we have 10 minutes left, right? So let's use up this 10 minutes some useful way. Okay, so this, any question about this? So we stop the debug mode. We go out from MATLAB, stop the sharing, and we go to some new sharing. Okay, so what we would do in the next class, let's take those things first. Okay, so let's see here. So in the next class, what we will do, we will go for the numerical integration. Okay, so our next class will be, we will start with the numerical integration process. And there are, I mean, starting from the very simple method, like the Euler's method of integration, which we will do by our hand coding by MATLAB. There are other higher order complex methods for numerical integration. Okay, like the Runge-Kutta method. And another advancement of Runge-Kutta is the Runge-Kutta-Gill method. And of course, in MATLAB, you have some solver of ordinary differential equation systems, or systems of ODE. Like there is ODE 2.3. There is ODE 4.5. And of course, each of them have their own application. So what I will do, I will probably do the hand coding first using the Euler method or the Euler method for numerical integration. And then I will give you the assignment to solve the same with ODE45, okay, which is built in MATLAB. That's the ODE solver. So what would you get? Just before I finish, let me give you some a review on the numerical integration method used by the Euler or proposed by Euler. So let's say if you have any differential equation of this form, x, let's say x1 dot equals x2 plus x1, something like that. And let's say it's a second order ODE, x2 dot, and it is, let's say, nonlinear, e to the power x1 into x2. Just take an example. This is our second order ODE. So how do you apply the Euler's method to this second order system to get the responses like x versus time and x2 versus time? So simply the method, the technique that was adopted by the Euler is this. So if you have any differential equation of this form, dx over dt in general. So what you do, and this is some function, okay? Let's say we take the first one here, that is x1 plus x2. So this is dx1 over dt, that is x1 plus x2. And if I follow this method, then what I do, simply I take this dx1 over dt as this. So I can write in some, with the help of some indexing, okay, x1. What is the meaning of dx1? Dx1 means it is the change in x1, right? Some change in x1. So any change in any variable, of course, can be written in this manner with the help of the indexes or indices. So xi plus 1 minus, sorry, x1i plus 1 minus x1i, and dt, you can also write it like this, ti plus 1 minus ti, right? So the numerator is written in terms of the difference variable. The denominator is written in terms of the difference variable. And that is equal to, we can say, x1 of I plus x2 of I. And then what we can do, if we can say, if we know all the variable values at the ith index, then this can be calculated. Xi plus 1 can be calculated. So what we do, we simply write it like this. Xi plus 1 is nothing but x1i plus, so this ti plus 1 minus ti, we can also write it in terms of dt or delta t, all the same, multiplied by whatever we had on the right hand side. This is simply the Euler's method of numerical integration, very simple. So that means if you know this sampling time, okay, these are the sampling time or the instants or discretization step, we can say discretization step for solving the system of ODE. So if I know xi at the ith instance, if I know x2 at the ith instance, and these are same, if I set this del t to some value according to my requirement, okay, if I want more steps in my plot, then I will take delta t small, so that the points here on the final plot of x1 versus time would be much closer. Okay, if I take very close or very small value of delta t, sampling time, this is known as the sampling time or discretization step of your solution. And if you take delta t very large, then there will be again some problem. So there is basically a trade-off how you should choose these delta t. Okay, you can't go for very small value, even you can't go for very large value. So there is a trade-off. We'll choose some intermediate value. I'm not going into the trade-off part there because that should be covered in your numerical integration technique. So in short, if I know the ith indexed values, then I can calculate the I plus 1th indexed values. Similarly, for the next equation, I'm not going to go the detail for that into the detail of that. So I'm going to write simply x2 I plus 1 can be calculated if I know x2 I plus delta t multiplied by x2 I again, because that is the expression of x2 dot e to the power x1 I. So that's it. Okay, so that means these are the iterative steps for equation number 1. This is the one. For equation number 2, this is the one. And that is the Euler method of numerical integration. So what are left to be known for this model? The things that are left to be known, number 1 is delta t. Okay, so we will see in the simulation in the next class, inshallah, in MATLAB platform, that how we choose or what value should be chosen, what is the reasonable value for our simulation purpose for our system of SMIB. So delta t we will choose. Another thing that is left is you should start from some initial value. When I is equals to 1, that is your first value, first set of value for x1 and x2, right? So you should know what is x1 at I equals to 1 and x2 at I equals to 1. That is the initial set of value for x1 and x2 for this second order system. And for SMIB, we have already done it. So we don't have to bother about the initial value calculation anymore. So we know these values now for our SMIB system. But for solving this second order system, you have to know what is x1, the first iteration, and x2 at the first iteration. And then that means you know x1 value when I equals to 1 and x2 value at I equals to 1. And then once you know this, you can calculate that second value of x2. Once you know the second value, then you can go for the third value and so on. Okay. Another thing that you have to set is the total simulation time. Okay. For how long you are going to simulate the response. Okay. So with this little introduction to the numerical integration method of Euler, we are going to stop today's lecture, and inshallah on Friday we will start from here, that how we will apply the Euler method for the SMIB system. Okay, so that's it. Any question? Any confusion? No question. Okay, so that's it then. Inshallah we see
Please,
you.
sir.
Yes.
We have classes 2 times a week.
Yeah, we have classes 2 times a week, and I usually post the class links on the Google Classroom.
I don't know. And Friday, what time is the class? Please?
Friday at 8 a.m. Inshallah.
8 a.m.
8 a.m. Yes, you will get the link in the Google Classroom in due time.
So you know I'm in Cameroon, right?
But you can access the Google Classroom, whether at least if you are in the world, within the world, at least if you're not in the moon, if you are within the earth, inside the earth, you should be able, and if you have the access of internet, right? But
okay, so it's because it's at night time here in Cameroon. 8 a.m. is night time.
Okay. I see. But actually we set it, I mean, before you actually joined the class, so I didn't think about your case. We have another student from Ayman from Palestine, right? Oh no, not Ayman. We have Aldi. Aldi, are you there?
Yes, sir.
But with Indonesia, we have 2 hours gap, I think.
1 hour gap.
1 hour, so it's
Yes,
early in
it's
the
okay.
morning, but it's okay.
Yes.
So the problem is with one of our students. So, but life will go like this. Don't worry, this is online world, so your video lecture will be there, inshallah. And again, if you feel any problem, don't hesitate to contact me. Okay, don't hesitate.
So which version of MATLAB you are using?
Sorry, MATLAB version.
Which version you are using?
This is MATLAB 2019A. Okay, it's not the latest one. Okay, not 2020, just 2019. 2009. But the commands that I'm using, actually they are general. So any version, any earlier version should not cause any trouble. Okay. shouldn't cause any trouble. Okay, then. Thank you very much. Inshallah, we see you on Friday, early morning. Assalamu alaikum.